Hello everyone, and thank you for joining us. Welcome to the Thin Film TPT, Tool Package Training course at DTU Nanolab. The course consists of several lectures covering physical and chemical deposition methods. Before we start, we would like to introduce our team. At the Thin Film Group at DTU Nanolab, we are a team of process specialists, Pernille, Rebecca, Potama, and Yevgeny. We are responsible for the thin film tools and share responsibilities among ourselves. Additionally, we have skilled technicians, including Henrik, Franco, Fleming, and Pete, who handle hardware problems, perform equipment maintenance, and ensure smooth operation. You can find our email addresses below. For process-related questions, you can email the Thin Film Group at DTU Nanolab. For training requests, email training@nanolab.2.dk. This email is for training in thin films and other areas, including lithography, etching, characterization tools, and wet chemistry. Your request will be directed to the appropriate person responsible for the specific tool. Before you receive authorization to use our equipment, you must undergo proper training. We typically provide 2 training sessions for each piece of equipment. After completing the training, you will be authorized to book and use the equipment yourself. Authorization is managed through our electronic lab manager system. If you do not use the equipment for approximately 9 months, your authorization will automatically expire. For any equipment-related issues, you can find contact information in the lab manager. There is a drop-down menu where you can select the equipment and see the names of responsible staff members who can assist you. The course is intuitively divided into modules that cover different aspects of physical and chemical deposition. Each topic has its own video. In this lecture, we'll introduce the practical aspects of thin film deposition, define the term thin film, discuss formation mechanisms, and review key properties. Alright, let's begin with the introduction. Thin film formation. Why do we need thin films? They're fundamental to micro and nano fabrication, serving many roles, including microelectromechanical systems, MEMS, optical applications like developing transparent conducting oxides, such as indium tin oxide ITO or aluminum-doped zinc oxide AZO, or waveguides in photonics research, electrical applications, including transistors and piezoelectric devices, such as aluminum nitride or zinc oxide. Metallic contacts in devices, made through simple processes like evaporating aluminum or gold. Magnetic layers, involving the sputtering or evaporation of materials like iron and nickel. Chemical applications. Doping sources, adhesion promotion, and surface bonding. What is a thin film fundamentally? Typically, you deposit a thin film on a substrate such as a silicon wafer, glass, fused silica wafer, or sapphire. There are also substrates, such as indium phosphide, used in the DTU photonics department. The deposition begins with atoms arriving on the surface, forming separated islands. As deposition continues, these islands migrate and eventually create a continuous layer. When a layer is a few nanometers to micrometers thick, it is considered a thin film. Thin films have unique properties compared to bulk materials due to their high surface-to-volume ratio. They can exhibit different densities, optical, and electrical properties. As the material becomes thicker, it begins to exhibit properties more like those of a bulk material. Various methods and techniques have different boundaries and ranges for this transformation from thin film to bulk properties. Alright. Now I'm going to talk about the mechanism of formation. Imagine you have a substrate, possibly with defects like terraces, roughness, or grains. When an atom arrives, different things can happen. The incoming atom can re-evaporate immediately, or it can travel along the surface and meet a neighboring atom, creating a metastable island. While these islands are small, they are not very stable and can separate quickly. Atoms can continue migrating along the surface, forming bigger islands as more atoms arrive. At some point, atoms start being absorbed by larger clusters, which become permanently stable. Besides surface mobility, other effects, such as chemical affinity or diffusion into the substrate material, can occur. Finally, atoms can be captured by grain boundaries, terraces, or the roughness of the substrate. This mechanism of growth formation can be illustrated by imagining a droplet of liquid on a flat surface. If the molecules in the droplet interact strongly with the substrate, much stronger than the interactions between the liquid molecules themselves, the liquid will spread over the substrate, reducing the contact angle to almost zero. This is known as Frank van der Merwe growth, resulting in layer-by-layer formation. If the interaction between the atoms in the liquid droplet is much stronger than their interaction with the substrate, the droplet will maintain a well-defined curvature, and the contact angle will increase. This results in island growth formation, known as Vollmer-Weber growth, as seen when depositing gold on a glass surface, where the gold can be wiped off with isopropanol due to poor adhesion. The third case, Stransky-Krastanov growth, is an intermediate scenario in which strong attraction between particles and the substrate initially creates a smooth layer, but as the layer grows thicker, roughness becomes more pronounced. Most thin film deposition techniques require some degree of vacuum. The exception is thermal oxidation, which will be covered in the following lectures. The following part of the course focuses on physical vapor deposition, which requires ultra-high vacuum equipment. Even sputtering, which operates at a few milliliter, requires the chamber to be evacuated to ultra-high vacuum before the process. Different deposition methods require different pressure levels. For chemical or atomic layer deposition, you operate in a low vacuum regime and typically don't need advanced pumping equipment. However, for sputtering or evaporation methods, your chamber should be equipped with turbomolecular or cryogenic pumps. The image also provides information on vacuum levels, expected molecule density in 1 cubic centimeter, and the mean free path of particles at given pressures. Now, we would like to briefly discuss material properties. We have selected 6 topics to explain now. This list may not be exhaustive, but it is based on typical questions users ask during training sessions. The topics include step coverage, crystal structure, stress values, electrical properties, optical properties, and chemical composition. Let's start with step coverage. Imagine you have a substrate and perform a lithography process to pattern the photoresist, resulting in negative photoresist patterns. When you deposit a material, such as silver or aluminum, it covers the top and bottom surfaces, but not the sidewalls. You can then immerse the device in a dissolving solution to remove the photoresist, leaving only the material attached to the substrate. This is called the lift-off process. The lift-off process requires material deposition in a straight line towards the device to avoid deposition on the sidewalls. This is an example of bad step coverage, necessary for reliable pattern transfer. In contrast, conformal deposition on high aspect ratio structures creates a uniform layer on the top, bottom, and sidewalls. This is good step coverage, desirable in applications like passivating black silicon with an anti-reflective coating for solar cells. Different deposition methods provide different types of step coverage. Evaporation methods typically result in insufficient step coverage, while chemical vapor deposition, CVD, or atomic layer deposition, ALD, generally provide good step coverage. Sputtering can be tuned to achieve varying degrees of step coverage, but it's usually poorer than CVD and well below ALD. Here are some real-life examples. The first SEM cross-sectional image shows titanium and gold deposited on photoresist. The silicon substrate is at the bottom, with a titanium gold layer on top. The thin titanium layer acts as an adhesion layer for gold. You can see gold layers on the silicon and photoresist, but the sidewalls remain unaffected. This allows the photoresist to be dissolved, leaving only the gold layer attached to the silicon wafer. The second example shows excellent step coverage achieved by atomic layer deposition. The SEM image depicts zinc oxide deposited by ALD, perfectly covering the top, sidewalls, and bottom. The small gap between the coatings is due to sidewall geometry effects from reactive ion etching imperfections, not limitations in ALD. The second material property is crystal structure. There are three types of crystal structures you may encounter. 1. Monocrystalline, single crystal like a silicon wafer, with perfect atomic order on a large scale. A thin film with such order is called epitaxial or highly textured. 2. Polycrystalline, a thin film with many small grains, each with perfect order but randomly mixed. The SEM image shows titanium dioxide in the anatase phase, with visible grain boundaries. 3. Amorphous, no long-term atomic order. The SEM image shows amorphous titanium dioxide deposited on a silicon trench, with a featureless cross-section and smooth finish. You can also have mixtures of different crystal structures. Deposition method and parameters affect the output. For example, titanium dioxide deposited by ALD at 350 degrees Celsius is polycrystalline, while at 150 degrees Celsius, it is amorphous. Annealing can irreversibly convert amorphous films to polycrystalline films. X-ray diffraction can analyze crystalline phases and grain size. The third thin film property is stress formation. Thin films are subjected to some amount of stress. For example, if you deposit too much material on a wafer, it can crack due to stress, as shown in the image. Excessive metal coating in an evaporation chamber caused the wafer to flake. Thin film stress can cause bending, cracking, delamination, and void formation. The example shows cracks in a nickel film under significant stress. Another example shows stress due to annealing. Annealing titanium nitride at 900 degrees Celsius after depositing it at 500 degrees Celsius results in nanometer scale cracks. Sometimes stress can be used advantageously. For example, in cantilever fabrication, the cantilever rises after being released from the base due to stress relief, making it ready for use in a device. There are two kinds of stress, compressive and tensile. 1. Compressive stress. The film, in a stress-free condition, would occupy a larger area, but during deposition, it is constrained in a smaller area and wants to expand. 2. Tensile stress. The film, in a stress-free condition, would occupy a smaller area, but after deposition, it is forced to stay in a larger area, leading to stress. Stress can cause the wafer to bow. A wafer might appear normal but fail vacuum clamping when moved to another chamber due to surface curvature. Let's briefly discuss the electrical properties of deposited films. Typically, you will measure values such as resistivity, conductivity, and sheet resistance. These values can vary across the sample and are often thickness dependent. The electrical properties can be tuned by introducing a dopant, as in aluminum-doped zinc oxide films. However, the output can be affected by contamination, impurities, and other factors. We utilize a 4-point probe to analyze these properties. This allows us to measure sheet resistance at different positions on a wafer up to 150 mm in diameter. For applications requiring high-quality dielectrics, such as forming gate oxides in transistor devices, we monitor the dielectric quality by measuring the breakdown voltage. Any material becomes conductive at some point if a high enough voltage is applied. For instance, if you deposit silicon dioxide by a method such as dry or wet oxidation of silicon, you might end up with gases or defects incorporated into the film. When a voltage is applied, these traps, such as trapped gas atoms, moisture defects, or impurities, will arrange themselves into the shortest conduction path due to the electric field. If the voltage is increased further, eventually a breakdown phenomenon will occur, locally melting the silicon dioxide and creating a conductive tunnel. The voltage at which this breakdown happens is measured. A high breakdown voltage indicates a good dielectric, whereas a low breakdown voltage suggests contamination or defects. For example, if you deposited silicon dioxide but didn't clean it properly, such as not treating the wafer in piranha solution after wet etching silicon with potassium hydroxide, KOH, potassium ions can penetrate the silicon dioxide, significantly reducing the quality of your layer. Alright, let's talk about optical properties. When depositing a thin film, you may want to measure various optical functions. For example, you can measure permittivity, which is related to the refractive index and absorption coefficient. Additionally, you can measure transmission intensity, both polarized and non-polarized, and reflection intensity. You can also perform thickness evaluation using optical methods. These optical functions can vary across the sample and be thickness dependent if the sample is non-uniform. We have several tools for optical characterization. One is the CRAIC microspectrophotometer, which illuminates the sample in a normal incidence configuration, allowing spectroscopic polarized and non-polarized reflection and transmission measurements over the wavelength range from 400 nanometers to approximately 2 microns. Another excellent tool is the variable angle spectroscopic ellipsometer, used to measure dielectric functions, refractive index, and extinction coefficient, and to evaluate thickness. The example shows aluminum oxide deposited by atomic layer deposition, highlighting thickness variation across a 100 mm wafer and refractive index as a function of wavelength for different deposition temperatures. The last material property I'll cover is composition. Sometimes you'll be working with simple elements like silicon, gold, or aluminum. However, you may also deposit more complex chemical compounds, such as indium tin oxide or aluminum-doped zinc oxide. In these cases, controlling the atomic composition is crucial, as the film's properties are strongly dependent on the individual atomic concentrations. For example, when depositing silicon nitride, you can vary the proportion between silicon and nitrogen. If you aim for a perfect chemical silicon nitride with a 3:4 ratio, you achieve stoichiometric silicon nitride. However, if the silicon fraction is higher than 3, you obtain silicon-rich nitride, which has a higher refractive index but also higher optical losses. You can select the deposition recipe to achieve either pure stoichiometric nitride or silicon-rich silicon nitride, depending on your requirements. Stoichiometry refers to the proportions of individual elements in a compound and can be affected by deposition parameters. This image shows an example of aluminum-doped zinc oxide deposited using sputtering. By adjusting the pressure, you can see different atomic concentrations of azo components. Stoichiometry can also vary across the substrate due to non-uniformity issues. This variation can occur if reactive gases are present in the chamber with an uneven distribution or due to rotation factors. This is primarily a concern with larger substrates. Another important topic is surface oxidation after deposition. For instance, if you deposit aluminum, silver, or titanium, the surface can quickly oxidize upon exposure to air. This oxidation can create a moisture layer, forming an interface that may not be desirable for certain applications. For example, if you deposit an aluminum-titanium bilayer, breaking the vacuum between depositions can result in an oxidized aluminum interface between the layers. Ideally, such depositions should be performed in the same chamber to avoid this issue. This image shows an example of XPS, X-ray photoelectron spectroscopy, measurement of aluminum deposited on a fused silica wafer. The image depicts oxygen distribution throughout the sample depth. Initially, aluminum oxide forms on the surface due to oxidation after breaking the vacuum. As you etch through the layer and measure oxygen, you find almost pure aluminum in the middle, although some oxygen remains due to residual gases in the chamber. Finally, at the bottom, you reach pure silicon dioxide from the glass substrate, indicated by a strong oxygen signal. Lastly, let's discuss contamination. There can be traces of gases such as water and carbon compounds, as well as contamination from the source material in the vacuum system. Cross-contamination can occur, primarily if multiple metals are deposited in the same chamber. We perform regular maintenance to ensure the chamber is clean, but flakes can occasionally appear and cause contamination. Be aware of potential issues caused by previous users, particularly if volatile materials are introduced into the chamber. Always read the manual before training and check cross-contamination information in Lab Manager to know which materials are allowed in specific tools. Alright, now we would like to give you an overview of the techniques we offer at DTU Nanolab. This slide maps out the deposition methods we'll cover. Materials can be formed by growth, for example, thermal oxidation, or by deposition, which we group into chemical and physical processes. All of these will be covered in the following video lectures. Thin films can be made using the growth or deposition approach. The growth approach involves consuming the wafer material to create a thin film, such as turning silicon into silicon dioxide by adding oxygen. Oxygen can come as a gas or hot water vapor, diffusing through the silicon lattice and forming silicon dioxide. In the deposition approach, you bring the source material from outside and condense it on a substrate surface. For example, silicon can be deposited by chemical vapor deposition, in which silane gas decomposes on the wafer surface, forming a silicon film and hydrogen as byproducts, which are pumped away from the chamber. Before we continue to PVD, we would like to introduce our local wiki source, LabAdvisor. LabAdvisor is our local Wikipedia used for many purposes. It is accessible at labadvisor.nanolab.dtu.dk. In the left panel, you can select menus such as characterization, lithography, etch, thermal processes, and thin film deposition methods. Under thin film deposition, you can find tips and detailed information about various material depositions. You can also contribute to LabAdvisor by sending us your results to help other students. That brings us to the end of this lecture. Thank you for your attention. In the next session, we'll cover physical vapor deposition methods.